Hello and welcome to the CentORus Workbench Running Project section of the tutorials. My name is Kareem El-Sayed. In this section, we'll discuss how to run an existing project and how to monitor a running simulation and how to visualize simulation results. For that, we'll take the project SimpleMOS, which is located in the Applications library in the Getting Started section under SWB, and here it is. Now in the Applications library, the files are read-only, obviously, so before we can work with them, we need to copy them into our own space. For that, we can select Edit Copy, or Ctrl-C will work as well. Then we select a place where we want to copy it, and then we can either go Edit again, or we can right-click here and say Paste, or do Ctrl-V. So now that we've copied it, we can open the project by just double-clicking it. And then you'll see the project table here. And we see the tool flow starts with CentORus Process, followed by CentORus Device, and finally CentORus Visual. We have several parameters in the project. We have the gate length LG, for which we only use a single value. But for the doping concentration NVAL, we'll use two different values. The same with the gate oxidation time and the LDD dose. Finally, for the electrical characterization, we'll use two different drain biases, VD, either 0.05 volts or 50 millivolts, or 1 volt for the saturation. So we have a total of 4 parameters that have more than one value, so 2 values each. That gives us a total of 16 different experiments. Now each of the cells in the project table corresponds to a node, and each node is in a certain status, which is signified by its color. Here all nodes are white, which means here none. Well, that just means that currently these nodes don't have a status because we haven't done anything with the project just yet. So let's jump ahead to the copy of the same project which ran already. First, notice that the project symbol in the project browser is yellow. That means that the project ran successfully. And in the project you see now a number of nodes that are yellow as well. That means that these nodes ran successfully, and the status is, you see down here, done. When we click on a done node, the Node Explorer window opens. And right now I just want to focus on the fact that the files that are shown here that are associated with these nodes are called either pp12 or n12 something. Now pp stands for preprocess, these are the input files, and n stands for the node file. But what's with the number 12 here? Well, that is the node number. So let me close that, and to see the node numbers we can go to View, Tree Options, and then Show Node Numbers. So you see here is the number 12. Each node has a unique number, and all the files that are associated with that node have this node number. Now what's with these baby blue nodes? So it says here virtual. If we click on it, we see there's nothing. Well, that just means that these are no actual simulation associated with that node. They're basically just placeholder to mark the split point. So now let me clean up this node 13. I'll just clean that up, and then we run it. We'll talk about that in a bit more. I just want to get a quick start here, and as soon as it started running, we gonna abort it. Okay, so then you see the node color turns to this magenta color. It is aborted. And now if we run the subsequent node, again we just click the run icon. So the node will launch, and then, surprise, surprise, it turns red because it failed. Why did it fail? Because the files from the previous node, in this case, were not ready, and so that's why it couldn't run. Okay, so this is what I wanted to show you here. So let's go back to our original project, and let's just run this project all together. So we can go to Project, Run. So let's see, we want to run all nodes, that's okay. We want to run it on the local machine, that's fine too. So let's just press OK. So what is happening? So first you see the preprocessor works, so you see these virtual nodes get marked, then a number of nodes turn green. So the one that are in this green, which is pending, means that they just wait for a CPU to start running. Then there is other nodes which are in this lighter green, which is the status queued, which means they are ready to run, but they need to wait for the previous node to complete because they depend on output files. Then there is this bluish color, which means that they are running, and as soon as they're done, they will turn yellow. Let's give it a moment for the first to complete. So here in my setting, I set it up that I allow 3 nodes on the local machine to run at the same time. We'll show in a later tutorial how to do that. By default, it is only 1. So if you do that, you might see only 1 node running here. Okay, so you see some nodes have completed, the next node have started, but let's do something different. I go again to Project and I will abort it. You can also just type Ctrl-T. And then all the aborted nodes turn magenta. We saw that previously, so now we can start all over by going to Project, Operation, Cleanup. You will do that a lot, so you might just use Ctrl-L for that. That deletes all the output files. So now I want to show you how you can just run a single node. So say we click this node and we click this Run Selected Node. It was the same menu that we saw before, but now instead of all, you see here the number 12. Okay. And so the preprocessor will start, and then we'll launch this node. We can also click on a particular experiment and then click the Run button, and then you see it automatically creates a string of these node numbers that are needed to run this experiment, and we click OK, and it starts running. And of these long string of nodes, you see that most of them were virtual, so nothing happens there, but these 3 ones are actual nodes, so it starts the simulation. Now I can also click on a node and then maybe control click on a few others and then manually select which nodes I want to execute. I click OK. So now again we talked that in my setup I can run 3 nodes concurrently, so that's why this one wasn't started immediately, but luckily the first one just finished, so then the next one starts. Now let's take a closer look at the output files. Let me just pick this node here. Here you see all the files that are associated with this node. The pp file is the input file for the tool associated with this node. So here it's sdevice. We'll talk about that in a later tutorial. And then the n file are all the output files. And that depends on the tool. For sdevice, you typically have a PLT file, which contains the electrical characteristics, and a TDR file, which shows, for example, the carrier distribution in the device. And then another important one is the log file that shows you how the simulation is progressing. And you can also visualize the files that contain simulation results by selecting the node and then clicking this as visual icon. And then you see on this side the PLT file is loaded. So if we can go here and select gate outer voltage to X and drain total current to Y, and then we see the IV characteristic here, and the TDR file is shown here, and for instance we can look at the electron density. So that is one way to access this data. So let me close that again. Now to show how to run as visual nodes, let me skip over to the project we ran earlier. So here you can either click on a single node and use this run selected visualizer nodes together, and this will run the script associated with this node. And here you see it. But sometimes you want to compare how your changes in the input parameter affects the output. So for that you can again either manually click a couple of nodes and then click this node, or just as an alternative, if you have a very complicated setup, you may want to select nodes in a more systematic way. So you can go to select by expression, and then you can type in all because we want to look at all experiments. Then for all experiments we want to look at the last node, so this is this last. And then we only are interested in the saturation current, so we want the ones that corresponds to a drain bias of 1 volt. So if we click that, you'll see it automatically selects these nodes for us. So now we can click this icon, and then we see here for the different doses and oxidation time how the IV changes. And that's all I wanted to show you in this section.